Okay, let's get started. Let me take roll. Hersey,
Here.
Irani, Gilcrease, Becky, I think Luna Sanchez is here. Macias, McKinnon, Morris.
Here.
Powers.
Here.
Renfro, Salvador, and Spivey is here. All right, so we're going to start with chapter 15, which deals with acids and bases. And what you're going to find is that, especially in the latter part of this chapter, some of the principles that we learned in the previous chapter dealing with equilibrium will come into play. All right? So we're going to start from the fundamentals, acids and bases. You, I think, would have met some of these terms before that I'm about to get into. Let's talk about acids firstly. Certain properties that are exhibited by acids. They typically have a sharp, sour taste. That does not mean that you should be tasting acids in lab to find out if they're acidic, right? So I thought I should say that. Vinegar, for example, is a solution of acetic acid, and the sharp taste that's associated with vinegar is due to the acetic acid. And there are certain citrus fruits also which contain citric acid, like lemons, orange, and so on. All right? Another property, that is displayed by acids is that they react with certain active metals to produce hydrogen gas. Usually, we're talking about the metals in the first and second group, and maybe a couple of them in the in group 3. Those metals and some of the transition metals as well, they will react with acids to form hydrogen gas. They also react with carbonates and bicarbonates to produce carbon dioxide. All right, and this is something you can actually do at home if you have baking soda and if you add to it vinegar, or alternatively, if you add to it lemon juice or orange juice, you'll see bubbles being formed. The bubbles will be due to carbon dioxide being produced as a result of the reaction between the carbonate ion, or I should say the bicarbonate ion in the case of baking soda, and the acids in the vinegar or citrus juices. Bases are considered to be chemical opposites of acids, all right? They tend to have a bitter taste. Again, please do not go about tasting bases in order to find out about this firsthand. They tend to feel slippery if you get some on your skin. Again, this is something I wouldn't recommend that you do, but just to explain why that happens because the hydroxide ions from the base reacts with the oils. The oils contain certain compounds known as lipids, or more specifically triglycerides, and it converts the triglycerides into soap. So basically, it's producing soap, and that's why it feels slippery when you get some on your skin. And as it says here, many soaps contain bases, all right? Okay, so let's look at one particular definition of an acid, according to a fellow by the name of Arrhenius. And according to Arrhenius, and he came up with a definition for acid and a base, right? So according to his definition of an acid is a substance that when added to water produces H+, or alternatively can be expressed as H3+, right? In water, right? So let me just say that, get this out of the way. Okay, let me just say something here. So H+ is oftentimes what is represented in most textbooks, but hydronium ions, the H0+, is actually more accurate in terms of what actually happens when the H+ is dissolved in water. It reacts with water to form the hydronium ions. So I think I'll stick to using H0+ as what is produced when an acid is added to water, right? So an example of this is HCl. When added to water, it produces a hydronium ion plus the chloride ion, right? So according to Arrhenius, this is what an acid does. When you add it to water, it produces hydronium ions. A base, on the other hand, is a substance which, when added to water, produces the hydroxide ion, as you can see in this example right here, right? NH3, which is ammonia, when it reacts with water, it forms the ammonium ion and the hydroxide ion, right? So that's the reason why ammonia is considered to be a base according to Arrhenius, right? So as you can see here, the Arrhenius definition is basically based on what will happen when you add a substance to water, all right? So it's kind of limited in that respect. Now, what you'll find is that there are other definitions by other persons. And the one that we're going to talk about here is Bronsted, right? And Bronsted said an acid is simply a substance which donates a proton. A proton is basically the hydrogen ion. Let me write this down here. Am I the only one smelling something burning? You smell it? Okay, maybe it's just me, I don't know. Some sort of electrical. Anyway, okay. So a proton. Oh, you smell it now? No? Okay.
I'm trying to smell
Okay. Maybe it's me. So basically, according to Bronsted, an acid is a substance which donates proton to another substance, which would be a base, right? So according to the Bronsted definition, a base is a substance which accepts a proton, right? So in this particular case, water is not necessarily a part of the definition, as in the case of the Arrhenius definition, right? In fact, water can be an acid or base based on the Bronsted definition. For example, going back to the reaction between ammonia and water, right? In this particular case, because the water is giving up a proton to the ammonia, the water will be considered to be the acid in this case, and the ammonia will be considered to be the base, all right? And then you're going to end up with the ammonium ion, right, which is itself acidic, and the hydroxide ion, which also itself is basic. So therefore, we can have a situation where the ammonia, which is a base, will be converted to an acid, and the water, which is an acid in this reaction, will be converted to a base. In fact, the term that we use for the products that are formed as a result of the acid-base reaction in this particular case, we call the base that is produced a conjugate base of the original acid, and the ammonium, we call it the conjugate acid of the original base, right? So the term used to describe this relationship, we call it a conjugate. In fact, let me see if I have it here. No, I don't. Okay. We call it a conjugate acid base pair. All right? So basically, you'll notice here that in the case of the ammonia, right, it gains a proton to form the ammonium ion, right? So the ammonia is said to be the base, or I should underline that there, and the resulting acid that is formed as a result of the gain of the protons by the ammonia is called the conjugate acid, all right? On the other hand, the water, which loses a proton, is considered to be the acid in this case, and the result of the loss of that hydrogen ion or proton is called the conjugate base, all right? So we call this here, going from here to, going from here to here, right? The hydroxide and the water is considered to be a conjugate acid-base pair. Acid base pair. And the other base pair, conjugate acid base pair, would be here. So that's the other conjugate acid base pair. All right? So that's the relationship between the acid and the conjugate base, or the base and the conjugate acid. All right? Okay, so that's the Bronsted definition. All right, so the Bronsted definition is not as limited as the Arrhenius definition, because you don't even need water to be involved, all right, in order to establish what's an acid, what's a base. In this particular case, the acid or base is dependent on what is accepting protons, which would be the base, and what is giving up protons, which would be the acid. Okay, even in the case of water, we have that type of reaction taking place, right? Water by itself, water not even reacting with anything or nothing dissolved in water. Now, if you get any sample of water, this is the equilibrium that will be discovered or established in water. The water molecule will undergo dissociation to form H plus and OH minus. They call this the autoionization of water, all right? So that happens in pure water if there's nothing added to it. In fact, to be more accurate, this is the reaction that is actually going to take place, which is shown down here, right? Here we have two water molecules, and what happens is that this water molecule will gain a hydrogen ion from the other water molecule. So the result is the structure that results from the gain of the hydrogen ion would be this, which is the hydronium ion, and the other structure, which is formed as a result of the loss of the hydrogen ion, is the hydroxide ion, all right? So in this case here, the first water molecule, right? In this case here, this would be the acid, in this case, and this molecule will be the base, all right? And that's because this hydrogen ion here will be transferred to that oxygen, and you end up with this. So since this is the base, then this would be the conjugate acid of water. And this here would be the conjugate base form of water, all right? Of the second water molecule, okay? So even in the case of pure water, the Bronsted definition applies, all right? And this is just an equation showing you the same thing, all right? So this is the acid, this is the conjugate base of this acid, and the water here, which is the water here, which is the base, would form the conjugate acid of that base, all right? So that's basically what happens even in pure water, okay? So that's the Bronsted definition. Now there's another definition that we're going to meet later on, which is the Lewis definition, which is even more expansive because it will take into account compounds that cannot be defined as acids and bases according to either Bronsted or Arrhenius, all right? Okay, so first assignment in this chapter, let me hand this out now. Here you go. Here you go. And for you guys out there in Zoom, let me go ahead and publish this assignment now for you guys.
We haven't turned in the previous assignment?
I'll have to check into that. I thought I posted a deadline date. If I haven't, I will definitely do that. Let me here. Okay, so for you guys out there in Zoom, I'm going to publish assignment number 4 right now. Okay, so you guys out there in Zoom, you should be able to bring that up. I'm going to download it right now so that we can at least get started on this particular assignment together. Okay, so this is assignment number 4. First question is, label the acid A, the base B, the conjugate acid Ca, and the conjugate base Cb in each of the following reactions. So they're giving you 3 equations, and you are to determine, based on presumably the Bronsted definition, what's the acid, what's the base, what's the conjugate acid, what's the conjugate base, right? So let me help you out with the first one. In the case of the first one, now remember the definition of an acid according to Bronsted is the substance that donates a proton to a base, and the base is a substance which accepts a proton from the acid. So if you look at the changes that are taking place between the reactants and products, you'll see that the H2SO4 here would have lost a hydrogen ion to form HSO4 minus, right? So therefore, the H2SO4 would be the acid in this case, which means that the ammonia, which accepts the hydrogen ion or the proton to form the ammonia, would be the base, all right? So we have established what is the acid and the base on the left side of the equation. So when we get to the right side of the equation, remember now, the substance which results from the loss of a proton from the acid will now be the conjugate base, which would be the HSO4. So Cb will go here. And as far as the other substance, which is formed as a result of the base gaining a proton, that would be the conjugate acid. So I'm going to put Ca here, and that's it. All right? Any questions about that? Any questions? Okay, what about B? If you understood what we did in A, then what would you say is the acid in the case of B? Exactly, so this would be the acid, HC2H3O2, which means that the water would be the base, all right? So let's look on the right side now. Which one of the two would be the conjugate acid of the base on the left side? Which would be the conjugate acid? H0 plus, exactly. So this would be the Ca, and which means that this would be the Cb, which is resulting from the hydrogen ions being lost by the acetic acid. Okay, any questions about that? Any questions about what we have just done so far? If not, let's look at C. Now C is slightly bit more complicated, but the same underlying principles apply. So, based on what we have here, which of the two reactants would be the acid in this case? Which of the two reactants would be the acid? And you guys out there in Zoom, you can chime in. Remember, the acid is a substance which donates or loses a proton to the base, and the base is a substance which accepts the proton from the acid, all right? So you have to keep that definition in mind. So, based on that definition, which of the two reactants would be the acid in this reaction? Which reactant loses hydrogen ions? Loses hydrogen ions. HCl, exactly. So that would be A, which means that this would be the base. All right? Okay, so let's go over to the product side. Which of these two would be the conjugate acid? Remember, the conjugate acid is what is formed when the base accepts a hydrogen ion. So which of these two would be the conjugate acid?
H2CO3.
H2CO3, so this would be the conjugate base, which means that this would be the conjugate acid because this is formed when the hydrogen ion when the acid loses a proton, and that's it, all right? Okay, any questions about any of these? Any questions? Any questions? Okay, I take it it's okay for me to clear this, right? All right, let me clear this. Let me do this, and let me scroll down. Okay, now in this case, in the case of number 2, it's asking for you to give the conjugate base of each of these acids. So again, you have to keep in mind the definition according to Bronsted, right? Bronsted says an acid is a substance which loses hydrogen ions, and a base is a substance which gains hydrogen ions, all right? Okay, so for the first one, what would be formed when, turn on this here, HI, hydrogen iodide or hydroiodic acid, what will be formed when it loses a hydrogen ion? What's the formula? This loses H plus, right? So what would be the result when it loses H plus? I minus, exactly. What about B, NH4 plus? What is formed when it loses a proton, an H plus ion? NH3. What about C, H2CO3? What is formed when that loses a proton? HCO3 minus, and then what about HNO3? What happens what is formed when that loses a proton? NO3 minus, exactly, all right? And that's it. Okay, any questions about number 2? Any questions? Okay, let's look at number 3. Now number 3, it's the opposite. They're giving you some bases, I should say, and you're asking for you to determine what the formula for the conjugate acid is. So basically, you're asking yourself, what is formed when H plus is added to it, right? So let's start off with Cn minus. So what is formed when you add a proton to it? HCN. What about O2 minus? When you add an H plus to it, what would be the result? HO minus or OH minus, same thing. What about this one? This is called the acetate ion. So when you add H plus to it, what would be the result?
H4CO.
All right. Traditionally, it would be, since it's an organic acid, we put the the hydrogen at the end. So this should be COOH. All right. Okay, and I think there's one more. Scroll up. Yes, there's one more, NH3. Let me clear all this here. Okay, NH3. So what is formed? So just a reminder, this is ACN, this is HO minus, this is CH3, COOH. Okay, and then in the case of NH3, what is formed when it gains a hydrogen ion? NH what?
4.
4 plus, exactly. And that's how we do number 4. Okay, any questions? Any questions? Let me clear this. Let me see what's below. Okay, we can do that yet. All right, so let me go back to the PowerPoint. And now we're going to talk about some quantitative aspects of acidic and basic solutions. Okay, so let me just see. Okay, so we talked about the autoionization of water, and you'll notice that it's a reversible process. In other words, if you leave it long enough, you're going to have equilibrium being established between the water molecules and the ions on the right side of the equation, right? So we can write down an equilibrium expression for that reaction, just as how we have wrote down or determined equilibrium expressions for different systems in equilibrium. That is no less true in the case of the autoionization of water. So we can write down that Kc is equal to the concentration of H plus, or we could put hydronium here, times the concentration of OH minus divided by the concentration of H2O. Now, because we know that H2O is a liquid, right? As we said before, something we talked about in the previous chapter, because H2O is a liquid, we can basically say that the concentration of H2O is constant. So we can rearrange this equation to get Kc times the concentration of H2O is equal to Kw. And this Kw is a special constant, right? Which is equal to the concentration of H plus times the concentration of OH minus, all right? That Kw has a special name. It's called the ionic product constant, Kw, right? And it is temperature dependent. Typically, the value that we use for Kw is measured at 25 degrees Celsius. At 25 degrees Celsius, the ionic product of water, Kw, is equal to 1.0 times 10 to the minus 40, all right? So that's a constant value as long as the temperature is constant. It tends to increase as the temperature increases, but for all purposes, we'll be using this value measured at 25 degrees Celsius, right? So that's the ionic product of water, right? Now, if the concentration of hydrogen ions is equal to the concentration of OH minus, right? That means that this and this would be the same, which means that the concentration of H plus would be the square root of that. But before we get to that, by definition, the solution will be neutral. If the concentration of the H plus and the hydroxide ion are equal to each other, then the solution is neutral. You can have situations, however, where the concentrations are different. So if the concentration of H plus is greater than the concentration of OH minus, then we say that the solution is acidic, all right? On the other hand, if the concentration of H plus is less than the concentration of OH minus, then we say that the solution is basic, right? So basically, when it comes to aqueous solutions, there are three possibilities in terms of the level of acidity or basicity, right? It's either that the concentrations of H plus ions and OH minus ions are the same, in which case the solution is neutral. However, if the concentration of H plus is greater than the concentration of hydroxide, then we say that the solution is acidic. If the concentration of OH minus is greater than the concentration of H plus, then we say that the solution is basic, all right? So that's basically how we determine, based on the relative concentrations of H plus and OH minus, whether or not a solution is acidic or basic. So here's a question. It says, what is the concentration of hydroxide ions in an HCl solution whose hydrogen ion concentration is 1.3 m? Well, since we know that the ionic product is equal to 1.0 times 10 to the minus 14, which is the product of the concentration of hydrogen ions and the hydroxide ions, then basically all we have to do is rearrange this equation to find the concentration of OH minus. We're given the concentration of H plus, right? So all we have to do is rearrange the equation like this, and therefore all we have to do now is plug in 1.3 where the concentration of H plus is. We plug in the ionic product of water, which is always constant at 25 degrees Celsius, and this is what we end up with. Actually, this should be 1.0 here. In any case, it's 1.0 times 10 to the minus 14 divided by 1.3, which is the molarity of the H plus. And according to the calculation here, the resulting concentration of the hydroxide would be equal to 7.7 times 10 to the minus 5, all right? So that's basically how you would solve this particular problem. Okay, any questions about this? Any questions? Okay, so based on what we have just done, let me just check something here. All right, so based on what we have done just now, we should be able to do question. Oh no, we can't do question. Okay. We can do question 7. So let me bring that up on the screen. So according to question 7, if a solution has an H plus concentration of 4.5 times 10 to the minus 7, is this an acidic or basic solution? What do you think? Keeping in mind that, let me give you a little hint here. The equation that would come into play here would be Kw, which is equal to 1.0 times 10 to the minus 14, is equal to the concentration of H plus times the concentration of OH minus, right? So remember also that if concentration of H plus is greater than the concentration of OH minus, then the solution is acidic. If the concentration of OH minus is greater than the concentration of H plus, then the solution is basic. Okay, so that's my hint. That should help you to answer this question. So they gave you this. They gave you that the molarity of the H plus solution of the hydrogen ions is 4.5 times 10 to the minus 7. So question is this solution acidic or basic? Why do you say that?
It's the concentration of H plus.
I'm sorry?
Is the concentration of H plus hydrogen plus ions are higher
Higher than what?
than 1.0 times 10 to the negative.
Higher than 1.0 times 10 to the minus what? No, that's not the reason why. I thought you were going to say something else. It's higher than something, but we haven't got to that yet. Basically, all you have to do is determine, well, one way of doing it, let me put it this way, one way of doing it is determine the concentration of OH minus, right? Which will equal to Kw divided by concentration of H plus, right? So Kw is 1.0 times 10 to the minus 14, and the concentration of H plus is 4.5 times 10 to the minus 7. So let me get my cheap calculator here. 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 7. And according to my calculation, this works out to be equal to 2.2 times 10 to the minus 8, right? M. Okay? So you're right about the fact that the solution is acidic, because when you compare the 4.5 times 10 to the minus 7 to the 2.2 times 10 to the minus 8, that tells you that the concentration of H plus is greater than the concentration of the OH minus. So therefore, the solution is acidic, since concentration of H plus is greater than the concentration of OH minus. There's another way of looking at it, but I'll get to that particular topic later on. But this is one way of doing it, which will be just as correct. All right? Okay, any questions about this? Any questions? Any questions? Okay, so let me clear this and go back to the PowerPoint. And let's talk about how do we quantitatively measure acidity. We measure acidity using the definition of pH, right? pH is basically a measure of the acidity of an acid solution, or of a solution, let me just say, of any aqueous solution. And this is actually the definition of pH. It's an equation where the pH is equal to minus log of the concentration of H plus, right? So going back to what we said before, if the solution is neutral, remember we said that in that particular instance, the concentration of H plus would be equal to the concentration of OH minus, which means that at 25 degrees Celsius, the concentration of H plus would be equal to 1 times 10 to the minus 7, right? If the concentration of H plus is equal to 1 times 10 to the minus 7, that means that the pH is equal to 7, all right? So in a neutral solution, the pH is equal to 7. Now, if the solution is acidic, that means that the concentration of H plus will be greater than the concentration of H minus, which means that the concentration of H plus will be greater than 1 times 10 to the minus 7, which is what I thought you were going to say when you were answering the question. If that's the case, then the pH of the solution will be less than 7, all right? And then finally, if the solution is basic, then this will be switched around. The concentration of OH minus would be greater than the concentration of H plus, which means that the concentration of H plus would be less than 1 times 10 to the minus 7, which means that the pH would be equal to, or would be greater than 7, all right? So basically, we can use the pH scale to tell whether or not a solution is acidic, neutral, or basic, right? And we could have used this to answer the question that we just looked at, right? In that, the number that was given was 4.5 times 10 to the minus 7, right? So basically, because 4.5 times 10 to the minus 7 is greater than 1 times 10 to the minus 7, then basically we can say that the solution is acidic. And if you were to calculate the pH using that formula, then you see that the pH would be less than 7 for that solution. All right? Okay, any questions about this? Any questions? Any questions? Okay, so basically this is the relationship in terms of trends and changes of pH as it relates to the concentration of H plus. As the pH increases, the concentration of H plus falls, right? And the reason why that is so is because of the negative sign right here, right? Because of the negative sign, there's sort of like an inverse relationship, well, more accurately, an inverse log relationship between the pH and the concentration of H plus. Another thing I need to mention also, which I don't think I have in any of the slides here, is that another way of describing this relationship is concentration of H plus will be equal to 10 to the minus pH, right? So this is used if you're given a pH and you need to find the concentration of H plus. So these are two different ways of saying the same thing, right? This is used to calculate the pH directly from the concentration of H plus. This is used to calculate the concentration of H plus directly from the pH, all right? Another thing I need to mention, and it has to do with significant figures, right? Which is very important when it comes to the use of the log functions, which is what is used here in calculating the pH. Basically, whatever the number of sig figs here, I'm going to put X here, X sig figs, right? The number of decimal places in the pH value calculated must be the same, X decimal places, all right? So that's very important as well, right? So for example, let's say, let me squeeze that down here. Let's say the concentration of H plus is 0.010 M, right? So this is 2 sig figs, right? So if you're calculating the pH based on this formula, pH will be equal to minus log of 0.010 M. So if you were to do that on your calculator, 0.010, and then log minus, on your calculator display, you're gonna have 2, but you have to express it to 2 decimal places, right? Because this number is expressed to 2 sig figs. So basically the answer here correctly would be 2.00, all right? Because you have 2 sig figs here, which means that your answer must be expressed to 2 decimal places. And this is true, as you're going to see later on, you'll be using the log functions for other things as well, but that's for later on. In any case, the same principle must apply, right? Whatever the number of sig figs of the number that you're applying the log to, the result should be rounded to the same number of decimal places, and vice versa, right? So for example, if you were given this to begin with, and you're asked to find this, because this is 2 decimal places, then the concentration of H plus must be expressed to 2 sig figs. So that is something that you need to keep in mind as well. Okay, any questions? Any questions? Any questions? Okay, so as you can see here, this is just a list of common fluids and their pHs, right? And we can actually measure the pH. There are 2 ways of measuring the pH in the lab, right? One is by the use of what we call a pH paper, right? A pH paper is basically a strip of paper that is soaked in a particular dye, right? Which is an indicator. And basically, there's also provided with it a pH scale where different colors correspond to different pH ranges, right? So therefore, what you do is dip your paper in a solution and compare it to the scale, and you can get an approximate reading of the pH. That is only used for approximate measurements. And in fact, oh no, you guys are Chem 2. My Chem 1 class will be exposed to using pH papers in the lab this afternoon. Were any of you in my lab from last semester? There was one experiment, sequence of chemical reactions. I don't know if you remember that, right? Which took 2 lab periods. In that particular experiment, I don't know if you recall, but you used an indicator paper, and they come in different ranges, right? So you can have a pH paper which goes from 1 to 12, and then you can have the ones that have a more narrow range, like from 1 to 4, or 5 to 6, or whatever, right? But that's for approximate pH measurements. Now, for more accurate pH measurements, we use what is called a pH meter, an example of which is shown here, all right? So this is basically consisting of, this is the device right here. Some of them are multi-purpose because you can use them to do other things depending on the software that comes with it, right? So, if it's that type of instrument, then you basically press a button which says pH, and it sets to measure pH measurements. And you have to do some calibration as well. So basically we have some solutions known as buffers. You're going to learn about buffers later on. Their pH is basically set. You put the electrode, which is this right here, into that buffer, and then you calibrate it according to the pH of that buffer, and then you take that electrode, you rinse it off with distilled water, and then you dip it in the solution that you're trying to measure the pH of, and then you're going to get your reading on your display up to 2 decimal places. So that is more accurate compared to using strips of pH papers. The pH papers, the most accurate would be 0 decimal places or integers in terms of pH units. But in the case of instruments like the pH meter that's shown here, it records the pH to 2 decimal places. And over here, you see a list of different solutions and their pH values. The gastric juice in the stomach, right? The pH is 1.0 to 2.0. That's pretty acidic, all right? And that's because of the hydrochloric acid that's present naturally in your stomach, which is produced by your stomach lining, which helps in the digestion of food, right? And then you have lemon juice, which is 2.4, vinegar, which is 3.0, and so on and so forth. Urine, which varies according to what you eat, from a low of 4.8 to a high of 7.5. And then water exposed to air. Now, this is interesting. One would think that water, of course, being water, would be neutral, therefore the pH is 7. But if it's exposed to air, what happens? It absorbs carbon dioxide. Carbon dioxide is an acidic gas. So as a result, the pH of water is not, well, water exposed to air, that is not 7, it's 5.5, all right? A bit acidic, or more acidic than pure water. And then we have saliva, milk, and so on and so forth. Milk of magnesia, which is 10.6, which is pretty high, and of course, ammonia being basic will have a relatively high pH of 11.5. So for most solutions, the pH ranges from 1 to 14. That's, even though you can have some extreme situations where it gets beyond those two extreme pH values, right? pH 1 would be like the most acidic, and then pH 14 would be the most basic, and then pH 7 is right in the middle, that would be neutral. Okay, another term that I want to introduce to you is what is called the pOH. And pOH is basically the opposite of pH. And here's the definition of pOH. It is the minus log of the concentration of OH minus. All right? And therefore, there's a relationship between the pH and pOH, right? Keeping in mind that this here is the relationship between H plus concentration, OH minus concentration, and Kw. Kw is equal to a constant, which is 1.0 times 10 to the minus 14. If you were to find the minus log of both sides, this is the result, right? Minus log of H plus minus the log of OH minus will be equal to 14.0. So when you put this in your calculator, you're going to get 14.0. You'd have to round this out to 2 decimal places because this started off with 2 sig figs, right? So what does this tell you? It tells you that the pH, which is equal to minus log of H plus the pOH, which is equal to the minus log of OH minus, is equal to 14.00, right? So basically, this equation will become useful in a couple of the problems that you'll be looking at when it comes to determining either the pH or the pOH, right? So basically what this tells you is that if you know the pOH, then you can easily calculate pH and vice versa, right? Because the sum of those two would be equal to 14.00. Okay, okay, here's a question here, an example. It gives you the pH of rainwater, and it's asking for the concentration of H plus, right? So remember, this is the equation here, which defines a pH, but we can rewrite it, as I said before, as this. The concentration of H plus is equal to 10 to the minus pH, all right? So all we have to do is put in the pH value of 4.82, where this is, and what happens? You're going to end up with 1.5 times 10 to the minus 5 as the concentration of H plus, all right? And again, just to reiterate what I said before about sig figs or decimal places, this value of pH is written to 2 decimal places, so therefore the concentration of the H plus would be to 2 sig figs, all right? Here's another example. Now in this case, they're asking for the pH of the blood, but they gave you this time the concentration of the hydroxide ion in a blood sample, which is 2.5 times 10 to the minus 7, right? Now, remember the relationship I just told you between pH and pOH, right? The sum of the pH and pOH is equal to 14.00. So basically, how we would solve this problem is that first, based on the pOH, we'll find the pH, and then we subtract it from 14.00, and that gives us the pH, right? So this is the formula for calculating pOH. All we have to do is put this molarity where we have the concentration of OH minus here, and we're going to get 6.60, so that's pOH. But the question is not asking for the pOH, the question is asking for the pH. So basically, we subtract the pOH from 14.00, and we get the pH of the blood, which is 7.40. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so one more thing I want to talk about, and then we'll get into the other assignment questions. Strong electrolyte, right? This is something that we learned in General Chemistry 1. A strong electrolyte is basically an ionic compound which undergoes complete dissociation. A good example of this would be sodium chloride. if you add sodium chloride to water and it dissolves, all the sodium chloride solid will be converted to ions. So what that means is that if you could actually see the particles, in addition to water molecules, you'll be seeing sodium and chloride ions floating around, right? You won't see any intact unit of sodium chloride present because all of it will be converted to ions, right? A weak electrolyte, on the other hand, does not undergo complete dissociation, right? A good example of this would be acetic acid, right? Acetic acid, only a small fraction of the molecules, when added to water, will convert to ions. And that's why we have this two-directional arrows indicating that basically this will be a system in a state of dynamic equilibrium, right? So you're going to have the forward reaction rate being equal to the reverse reaction rate, right? Now, strong acids are strong electrolytes, right? And since I have you three who were in my class before, you guys should be able to tell me what the 6 strong acids are, right? Sulfuric acid. 5 more. Let me see who out there in Zoom I've had before. Let me see. I had Spivey for lab. I had Joshua for a lecture, so he should be able to tell me as well. I don't remember if I had Mr. Kilcrease or Miss Luna. But you said sulfuric acid, right? Any other acid? 5 more.
Ionic acid.
What's that?
Ionic.
Ionic? No. That's not an acid. You're 6 acids. You're right about sulfuric. You guys need to remember these acids as strong acids. Sulfuric is one of them, and sulfuric is kind of special. I'll explain why shortly. But you're right about sulfuric. What are the other 5 acids? Because there are 6 of them. All right, let me give you a hint for a couple of them. Group 7. That's all I'm going to say about that. Group 7. Oh, let me see. Somebody said something in Zoom. Let me see who. Okay, Joshua said hydroiodic. Okay, so that's 2. And hydrobromic, that's 3. Okay. Hydrochloric, that's 4. 2 more. 2 more. Okay, just said hydrochloric, yeah. Nitric acid, right? 1 more. Perchloric acid. Thank you very much, Mr. McKinnon. So guys, you need to remember those acids. Let me write them down. Where shall I write it? Let me squeeze it in. Somewhere here. Okay, I'm just going to write them down in one line. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. Please remember these as strong acids, right? Those are the main strong acids that you will encounter. Okay, so strong acids, as I said before, are strong electrolytes. And one example of that would be, of course, hydrochloric acid, which when added to water undergo complete dissociation, right? So therefore, again, there'll be no intact molecules of HCl present in these solutions. Basically, you're going to have H3O plus and Cl minus ions floating around in a solution, all right? And you'll notice that the arrow here points in one direction, right? So it's not reversible. Another example of a strong acid would be nitric acid, right? Nitric acid does the same thing, undergoes complete dissociation to form ions, all right? Perchloric acid is a third example, undergoes complete dissociation as well in the same fashion, right? So that's how strong acids are. They're strong electrolytes. And because they're strong electrolytes, they can conduct electricity. Solutions of these acids will conduct electricity readily, all right? Okay, I promised you to mention something about sulfuric acid. As he said, sulfuric acid, strong acid. But you'll notice that in the formula of sulfuric acid, there are two hydrogen atoms, right? It turns out that the first dissociation is strong, right? So when the H2SO4 gives up one proton to the water, that would be a complete dissociation, right? Now, the thing is that the HSO4 minus itself is a weak acid, as you're going to see in this case right here. The HSO4 minus will lose the hydrogen ion to water, but this, you'll notice it's reversible, right? So the first dissociation is strong, the second dissociation is weak when it comes to sulfuric acid, right? And that will become important later on because sulfuric acid is not the only acid like this. There are other acids where they can lose up to 3 protons, right? And the dissociation in each case is different in terms of strength. So we're talking about here weak acids, right? These are weak electrolytes, so therefore they do not conduct electricity as well as in the case of strong acids, and that's because they all undergo partial or weak dissociation, as you can see in each of these examples, right? HF is a weak acid, hydrofluoric acid, undergoes partial dissociation to form the hydronium ion and the fluoride ion. And as you can see, it's a back and forth situation. So solutions like those are basically equilibrium systems, all right? Even water itself, believe it or not, is considered to be a weak acid, right? If you remember we said before, one of the water molecules will be performing the role of the base, the other water molecule will be performing the role of the acid. So basically when you have the proton transfer here, you're going to end up with the products being formed and it's going to go back and forth. So basically this would be a weak dissociation as far as water is concerned. Strong bases are strong electrolytes, all right? And again, you guys should know what the strong bases are. Let me save you the time. Basically, the strong bases are metallic hydroxides from groups 1A and 2A. Those are easy to remember as long as you remember that they belong to hydroxides of those two groups, right? So they undergo complete dissociation, as you can see in the case of sodium hydroxide. Sodium hydroxide will undergo complete dissociation to form sodium and hydroxide ions. And the same is true for potassium hydroxide, and the same is true for barium hydroxide. These are all strong bases, all right? Weak bases, on the other hand, undergo partial dissociation, and that is demonstrated by this example of the fluoride ion. It's a weak base because it does not produce hydroxide ions in great amounts because there's an equilibrium system that eventually will exist where it goes back and forth. So basically in the case of fluoride and other weak bases, the concentration of hydroxide ions will be relatively small. The same is true in the case of the nitrite ion and ammonia as well. Let me write that down. Ammonia, when added to water, I think I showed you this before, will form the ammonium ion and hydroxide ion, right? So these are all examples of weak bases, right? We talked about conjugate acid-base pairs before, and what you'll find is that there's some relationship between the strength of the acid, for example, and the strength of the base, or vice versa, right? And it turns out, and we can see some quantitative measurements of this, the conjugate base of a strong acid has no measurable strength. Basically, what you'll find is that the stronger the acid that we're dealing with, if you look at the strength of the base that is formed from it, the base is very weak, right? So if the acid is very strong, the conjugate base would be very weak, right? The hydronium ion, H0+, is the strongest acid that can exist in an aqueous solution. So what we're saying here is that if you have an acid that is stronger than the hydronium ion, then basically when you add that acid to water, that acid will be converted to or will react to produce the hydronium ion, right? In chemistry, we call this the leveling effect, right? Where the acidity of the strong acid is leveled to, or the solution will have a lower acidity compared to the strong acid that is added to it. And that's because the hydronium ion is the strongest acid that can exist in such a solution. The hydroxide ion, on the other hand, is the strongest base that can exist in an aqueous solution, all right? And here we have a list of different acids and their corresponding conjugate base. And what you'll find, as I mentioned before, as the acid strength increases the conjugate base strength decreases, right? So this arrow here shows you the direction of acid strength according to the list that is given here. And this shows you that the corresponding basic strength would be increasing in the opposite direction, right? So if you take a strong acid like perchloric acid, very strong, 100% dissociation, the perchloric ion is very weak. In other words, this, when you add it to water, pretty much will not produce any hydroxide ions, right? And as you find that the acid strength decreases, then the strength of the corresponding conjugate base would increase until you get to something like ammonia, where ammonia is considered to be among these compounds the weakest of acids. The amide ion, as a result, will be a very strong base, all right? Okay, so that's what's basically showing you the relative strengths of conjugate acid-base pairs. And this is just a diagram representing the difference between a strong acid and a weak acid. So as we said before, hydrochloric acid is an example of a strong acid. When you add it to water, all the HCl molecules will be converted to hydrogen ions and chloride ions, right? So this is before ionization, and then at equilibrium, basically you'll have no HCl molecules present. The only thing that will be present would be hydrogen ions and chloride ions. On the other hand, in the case of hydrofluoric acid, when you add it to water, what happens? The concentration of the HF does not change much, and the concentration of H plus and F minus are relatively low, right? And that's basically the difference between a strong acid and a weak acid. The strong acid will undergo complete dissociation, and therefore the concentration of ions will be relatively high, while the weak acid will undergo partial dissociation, and therefore, as a result, the concentrations of the ions will be relatively low. Okay, let me just continue here. Okay, so this question is asking, what is the pH of a 2 times 10 to the minus 3 M nitric acid solution? Did I show the work here? Okay, so first thing you have to ask yourself, if it's an acid, is it a strong acid or a weak acid? Because that is an important difference. And you're going to see that difference later on. But for now, we know that nitric acid is a strong acid, right? So because it's a strong acid, it undergoes 100% dissociation, which means that whatever the molarity of the nitric acid originally was, the molarity of the hydronium ion would be the same, because basically you have 100% conversion of the nitric acid to the hydronium ion, right? So basically all we have to do is, let me just show you. So this is the start where you had 2 times 10 to the minus 3 M of nitric acid. Initially you had no hydronium ion, and then at the end of this process, you'd have no nitric acid, but now you're going to have 0.002 M of the hydronium ion. So basically, to find the pH, we just put this value where the concentration of hydronium ion is, excuse me, in the formula, do your thing on the calculator, and you get the answer, which is 2.7 in this case, right? Again, you have 1 sig fig here, which means that you must have 1 decimal place expressed in the final answer. What time is it? I'm losing track of time. Oh, shoot. Having too much fun. All right. Any questions about this example? Any questions? Any questions? Here's another example. What is the pH of a 1.8 times 10 to the minus 2 M barium hydroxide? Again, you have to ask yourself the question, is this a strong base or a weak base? We all know, based on what I told you before, barium hydroxide barium is from group 2, right? So barium hydroxide would be a strong base, right? However, you have to be careful because you have to look at what happens when the barium hydroxide undergoes dissociation, right? It undergoes 100% dissociation, but please note that for every mole of barium hydroxide that dissolves, the moles of hydroxide that is produced is 2, right? So for every 1 mole of barium hydroxide that dissolves, 2 moles of hydroxide ions are produced. So you have to take that into account. Initially, you would have 1.8 times 10 to the minus 2 M of barium hydroxide. You would have no barium ions or hydroxide ions. And then when the reaction is completed, you're going to have no barium hydroxide present. You're going to have 0.018 M of barium ions present. But here, you're going to have 2 times 0.018, which will be equal to 0.036 M, right? So to find the pH, now remember, the question is asking for the pH. What we have here is the concentration of OH. To find the pH, what we have to do first is to determine the POH, right? The POH would be minus log of this, and then we subtract that from 14.00 to get a pH. So that is done, those two steps are done in this line right here. And the final answer here is 12.6, and that would be the pH of this solution. All right? Okay, any questions about this one? Any questions? Any questions? Any questions? Okay, let's see here. Okay, so based on what we have covered so far, and we probably only be able to do one or two of these questions in class, based on the fact that we have 15 minutes remaining. Let me go back to the assignment. So now we should be able to do question 4, 5. Hold on, let me see here. We should be able to do question 4, 5, 6. We did 7 already. 8. Okay. Oh, I screwed up on the numbering system. Oh, this is 6. I'm sorry. We should be able to do 6, 7. Okay, so basically all the questions from 4 to, oh, I did screw up the numbering system. I'm sorry about that, folks. There's 2 number 6 and 2 number 7s. There's 1 number, no, right. So there are 2 number 6. So you should be able to do all the questions up to the second number 7. Sorry about that. Okay, so we won't be able to do all of them, so I'm just going to do as many questions as I can. So the first question, number 4, says, what is the pH of a solution that contains 25 grams of hydrochloric acid dissolved in 1.5 liters of water? Now, let me remind you, let me squeeze it up here, that the formula for pH is equal to minus log the concentration of H plus, right? That is the formula that you're going to use. So what's the first question you'd ask yourself? We did a couple of examples before, just before now, all right? And what did I say the first thing you have to ask yourself? It's a strong acid, right? And of course, hydrochloric acid is a strong acid, right? So we know that hydrochloric acid will, when added to water, will give hydronium and chloride ions, right? It won't be a back and forth, right? The reaction will go one direction, all right? Okay, so basically what we need to do is find the concentration of hydronium ions present to find the pH, right? So how would you think we go about doing this? We have to start with the 25 grams of the HCl. What would you do with that number? 25 grams of HCl. Excuse me. Oh, and by the way, remember, because HCl is a strong acid, whatever the molarity of this is, the molarity of this in the solution will be the same because of the 1-to-1 ratio, right? Okay, so again, I ask the question. You're starting off with 25 grams of HCl. So what would you do with this 25 grams of HCl and also the 1.5 liters of water to determine the pH? Let me give you a hint. You have to use the conversion factor right there.
Moles.
Convert to moles, right? So you need a molar mass of HCl. So again, because I'm lazy, I'm going to go to my trusty old molar mass calculator. In the case, oh gosh, what's this here? HCl. Okay, 36.46. So so 36.46 grams of HCl will go down here, and 1 mole of HCl will go on top. All right. Okay, so we have converted by doing this step the grams of HCl to moles. So what's the next step? Convert it to what? Molarity. How would you do that? how would you go from moles, whoops, I'm sorry. I clicked on the wrong button. Okay, I remember this. Okay, so how would you, oh shoot, did I erase? Oh my goodness, okay, let me rewrite this here. I'm sorry about that. So this should be 25 grams of HCl multiplied by 1 mole of HCl divided by 30, what was it, 35? What was the molar mass of HCl? 36, did anybody write that down? 36.46 grams of HCl, okay, thank you. Okay, so you're correct, you need to get from here, because the grams will cancel out, you're gonna end up with the moles of HCl. So how would you go from that to molarity? Divide by the 1.5 liters, 1.5 liters, right? And that will give you the molarity. So let me 5 divided by 36.46 divided by 1.5. And according to my calculations, rounded off to 2 sig figs, you're going to get 0.46 m, right? So that would be the molarity of the HCl, which would be the same as the molarity of the hydronium ion. So therefore, the pH of the solution would be equal to minus log of 0.46. And let's see what that gives. So 0.46 log minus, and according to my calculation, the answer here would be, since this is 2 sig figs, this has to be expressed to 2 decimal places. So this would be 0.34, and that would be the final answer for that one. All right? Any questions? Any questions about this one? Okay, if you understand number 4, then you should be able to do number 5. It's pretty much the same thing. The only difference is the mass. Well, it's a different acid, which won't make a difference in the, well, yes, it would, because you need a different molar mass. So you're given a different mass, you're given a different molar mass, and you're given the volume in milliliters, which means you have to convert to liters. And then you do just like we did in question number 4, right? So I'm going to leave you to do that one on your own. I want to see if I can do number 6. Squeeze in number 6 quickly. This page will contain 1.2 moles. Okay, let's do this one quickly. So basically you're mixing 2 acids, 1.2 moles of nitric acid, 1.7 moles of HCl, right? And you're dissolving it in 1,000 liters of water. All right, so let me do this one quickly. So in this particular case, what I would do is look at the dissociation. Well, again, we have to ask ourselves the question, what type of acids we're dealing with here? Nitric and hydrochloric are both strong acids, right? So what I would do is, I would say that, well, because they're both strong acids, they both will release hydrogen ions, which will be equal to the moles of the original amount of each of the acids, right? So therefore, we can say that the total moles of hydronium would be equal to 1.2 moles plus 1.7 moles, which will be equal to 2.9 moles. All right? And then to get the molarity, that would be equal to 2.9 moles divided by the volume in liters. It says 1,000 liters. All right? I'll put a decimal point here just to make sure that this is expressed to 4 sig figs, right? The 1,000. So basically that would be equal to 2.9 times 10 to the minus 3 m, right? So the pH would be equal to minus log of 2.9 times 10 to the minus 3. Let's see what that gives. 2.9 times 10 to the minus 3, and then log, and then minus. According to my calculation, this works out to be 2.54 as your final answer. All right? And that's basically how that is done. All right? Okay, any questions about that one? Any questions? Any questions? Okay, so I'm going to stop here for today. I'm going to leave you to do the others. We did question 7 already. So I want you to try on your own question 6, 7. And that's it, all right? If you have any problems doing these, please feel free to come and see me, all right? Before you guys leave, I'm quite sure you have noticed that I've posted your test scores in Canvas. I'm going to send you, I didn't have the opportunity to scan them. So later on this evening, I'm going to scan them and send you your actual graded test, right? And I'll have a few comments to say about your collective performance, all right? So that's pretty much it for today, unless there are any questions. All right, so that's it for today. I'll see you guys on Wednesday.
Number 3, I do not think it's
Oh.
Canvas.
Thank you for reminding me. Assignment number 3, folks. Let me do a quick thing here. Thank you for reminding me. We'll do this. So let me go assignments. Okay, I need to open up a job for that. Let me go. Okay, so this is February 17th. So I'm going to make it due tomorrow. So make sure that you submit your assignment 17 by tomorrow midnight. Save. Okay, so now the Dropbox is available for you to submit assignment number 3. All right? Okay, that's it, folks. I'll see you guys on Wednesday.
What's the highest grade on the test?
Hold on 1 minute. According to my records, the highest grade was 79, and that was before the 10 points that I would add for Skype. So that person got 89. Yeah.
What was the average?
I didn't calculate the average, I'm sorry.
Okay, that's okay.
Yeah.
Just